Hello, welcome to part 2 of the top 100 most common networking terms you need to know. In this part we'll talk a lot about IP addresses in general, so let's get started right away. Number 11. Default Gateway. A term that might be a little confusing, especially when compared to a router or a gateway, and basically most of the time a router will be a gateway and a default gateway at the same time, but you should know the difference. So a default gateway is an IP address that is an exit point to other unspecified or unknown networks. If for example your computer wants to send data to a destination outside the local network, it will send it to a default gateway. This default gateway is usually the router's local IP address, for example 192.168.0.1. So a default gateway is the IP address of that device to which we send traffic when we don't know where else it should go. Number 12. Default route. A default route is a special route configured on a router that defines where to send packets with unknown destinations. So what's the difference between default route and default gateway? A default route is the entire configuration on a router that contains a default gateway. The default gateway is a single IP address, and the default route is the routing table entry that tells the router to forward all unknown traffic to the next hop. And remember, when we talked about routing, I told you that a router is looking for the best path for the packet to reach its destination. Routers store these paths in something called a routing table, and there can be many different routes configured to different networks. But we cannot have a route to all different networks in the world configured on one router. It would be impossible. And that's why we use a default route. So a default route is a special route that is used to route packets if the destination is not found. It means everything else. We configure it on a router by using the command iproute 0.0.0.0 0.0.0.0, and then we specify our default gateway, and let's say for example 192.168.0.1, and all the zeros mean any destination. So the router doesn't know where to send the packet, and then it will send it to the next hop at 192.168.0.1. So to summarize it, a gateway is any device that connects two different networks together. A default gateway is the IP address of the device that is used as the next hop to reach unknown destinations, and a default route is the routing table entry that points to the default gateway. Number 13. IP address. There are two types of addresses that each device has assigned: an IP address, which is a logical address of the device, and a MAC address, which is a physical address of the device, but about MAC addresses I will talk later in more detail. So an IP address is a unique identifier for each device in the network. It's like the postal address of a device, and it allows devices to communicate and know where to send data packets. Remember, on layer 3 of OSI model, the unit of data that we work with is called a packet. IP addresses are used on layer 3 of the OSI model, which is called a network layer. So we need an IP address for routing packets. Number 14. IPv4. This is the original implementation of IP addresses, and most likely this is how you imagine the IP address. It is nowadays still the most common implementation used worldwide. An example of IPv4 address is 192.168.0.1. So as you can see, there are 4 numbers separated by dots. Each of these numbers is called an octet. So an IPv4 address is made of 4 octets. As you know, computers communicate using zeros and ones, and an IP address is no different. IP address is just zeros and ones, so it's a binary number that is represented in a human-friendly form for us. So each octet is made of 8 bits. That's why we call it an octet. So let's slow down and let's try to understand it, because it's really important. So each octet has the maximum possible value of 255. You can calculate this by doing 2 to the power of 8, which gives us 256. So when we start counting from 0, 255 is the highest possible value for one octet. So if we go from the right, the last bit in an octet has the value of 1, and each next bit has always twice as big value. So first bit is 1, then 2, 4, 8, 16, 32, 64, 128. And if we sum it up, we are left with 255. So for example, an IP address 192.168.0.1 in binary is what you can see on the screen right now. So this 4 octets of zeros and ones. So if we have 4 octets and each octet is 8 bits, that gives us 32 bits in total. And 2 to the power of 32 gives us 4,294,967,296 possible IPv4 addresses. And even though it sounds big, as you can imagine, this is way too low nowadays, because almost every electronic device needs an IP address. And the thing is, when they implemented the IPv4, no one thought that we would ever need more than 4 billion addresses. It was enough at this time. But this number is just too low nowadays for the whole world. But there are also some solutions to this problem that I will discuss soon. Number 15. Public IP addresses. Okay, so there are public and private IP addresses, and it will all make more sense when you understand both of them, but let's start from the public ones. So basically, public IP addresses are all addresses that are routable on the internet. These addresses are unique worldwide and they are managed by IANA, which assigns large blocks of these IP addresses to regional registries. And then internet service providers assign them to end users, so you get the public IP address on your router from your internet service provider. Public addresses can be directly accessed from anywhere on the internet, in contrast to private IP addresses, which are used only inside local networks. But as I mentioned before, there are too few IPv4 addresses available, so not every device in the world can get a unique IP address. And one of the solutions to that problem are private IP addresses. Number 16. Private IP addresses. So private IP addresses are addresses in the following ranges. And by the way, it's really important that you remember all of them, but also after some time in networking, you will recognize them immediately. Okay, so the first one, 10.0.0.0/8, so it's 10.0.0.0 to 10.255.255.255, so this whole 10 block. Then second one, 172.16.0.0/12, so addresses from 172.16.0.0 to 172.31.255.255. Then the third one, 192.168.0.0/16, so addresses from 192.168.0.0 to 192.168.255.255. And these addresses are defined in RFC 1918, one of the most well-known RFCs. The addresses in these ranges are always used only on private local networks. They are not routable on the internet. And so the reason of creating private IP addresses is what I mentioned already. There are too few IPv4 addresses available. But every node in the network needs an IP address, and private IP addresses solve that issue, because all networks in the world can just use these addresses in their local networks. Your computer also most likely has a private IP address assigned. I think it will be easier for you to understand if I give you some simple example. So a company A in New York can have assigned, let's say, the IP address 10.0.0.1 to one of their computers. And company B in Berlin can also have that same 10.0.0.1 IP address assigned to one of their computers. So these IP addresses still need to be unique within the same private network. So for example, you cannot have one computer with the same IP as the other, but they are obviously not unique globally, because everyone can reuse the same IP ranges for internal uses. However, as you remember, they are also not routable on the internet, so what to do about it? We still need to access the internet, right? And that's exactly where NAT protocol comes in. Number 17, NAT. NAT, which stands for Network Address Translation, is a protocol that is necessary for the private IP addresses to work. It allows devices with a private IP addresses to communicate with the public internet. What it does is translate private IP addresses into public IP addresses so that they can be routed on the internet. So let's say you have two computers on your local private network, and one of them has IP address of 10.0.0.1 and the other has 10.0.0.2. These are two private IP addresses, but when you want to access the internet, you need to use the public IP address. So both of these private IP addresses will be translated into one public IP address, let's say 150.100.0.1 or whatever address has been assigned to you by the Internet Service Provider. This is also called PAT, which stands for Port Address Translation, and is the most common version of NAT. So many private IP addresses share one public IP address, and the router keeps track of the connections using port numbers. Number 18. CIDR. CIDR stands for Classless Interdomain Routing, and to understand it, you need to know that back in the day there were 5 classes for IP addresses. You can see them on the screen right now. So Class A was used for very large networks, Class B was used for medium-sized networks, and Class C was used for small networks. Then we have also Class D, used for multicast, and Class E, used for experimental or reserved purposes. So what it means is that when a company was assigned an IP address block from the Internet Service Provider, they received one of these fixed classes. So if they got a Class A, for example 7.0.0.0/8, that's almost 16.7 million usable addresses, even if they didn't need so many, so all of these unused IP addresses would be wasted. In Class B, network/16, we would have 65,534 assignable addresses, and if company needed only 1,000 addresses, for example, then the rest, around 64,000, would be wasted. In Class C, which is /24 network, it would be 254 assignable addresses. So here comes the CIDR, which allows using variable subnet sizes according to each company's needs. So if a company needs, let's say, around 5,000 IP addresses, they can receive a /19 network from the ISP, which provides 8,190 IP addresses. You can go and Google the CIDR chart and see for yourself the complete list to see how many addresses are available in each network. I won't go into the detail now how to calculate all of that now. It's only so that you understand that the purpose of CIDR is to allow using a flexible network, so we don't have to be forced to use either /8, /16 or /24. We can use whatever we need. We're not limited. And it's also one of the solutions for the IPv4 exhaustion problem because it doesn't waste as many addresses as the fixed classes used to. Number 19. VLSM. VLSM stands for Variable Length Subnet Masking. So in order for the CIDR to work properly, we also need the VLSM. It might be a bit confusing at first, but it's important to understand the difference between these two. Because of the CIDR, we can receive any network size from the Internet Service Provider. Let's say we need /19, which gives us 8,190 usable addresses, and what VLSM does is allowing us to divide this /19 even further for our needs. So let's say the ISP gave us the network 102.0.0/19, which means the usable IP addresses are in the range 102.0.0.1 to 102.0.31.254. We can further divide it into smaller networks. For example, we need to have 500 IP addresses in one network, so we can use /23 network for that, which gives us 510 usable IP addresses. In our network, it would be 102.0.0.0/23, which means the usable IP addresses are in the range 102.0.0.1 to 102.0.1.254. And then if we need to use another network, let's say /24, we can do that, and we just start from where we ended. So the next network in our case would be 102.0.2.0/24, which gives us the usable IP addresses in the range 102.0.2.1 to 102.0.2.254. And thanks to the VLSM, we can divide our network however we like, and it's totally up to us, so we're really flexible here. Number 20. IPv6. One of the main solutions to the IPv4 address exhaustion problem is IPv6. As you remember, IPv4 is a 32-bit address, while IPv6 uses a 128-bit address. This is a gigantic difference. IPv6 gives us around 340 undecillion possible addresses, and this is a number hard to imagine. It's 340 followed by 36 zeros. It's such a colossal number that we could even assign one IPv6 address for every grain of sand in the world, and we still wouldn't run out of addresses, so just imagine how big it is. IPv6 is written in hexadecimal, and it's separated by colons instead of dots as in IPv4 address. IPv6 solves the IPv4 exhaustion problem completely, and you might ask, why don't we use it then? Well, the thing is, the migration is ongoing. IPv6 adoption is increasing every year, and eventually we will move to IPv6 only. But for now, most of the world still relies on IPv4, and as far as it works, a lot of companies don't want to switch to IPv6 because it takes time and costs a lot of money. Right now, most networks use something called dual stack, which means IPv4 and IPv6 can work together at the same time. Your computer most likely also have an IPv6 address. IPv6 also doesn't use NAT, the network address translation protocol that we discussed before, because there's simply no need to translate private to public IP addresses. There are so many IPv6 addresses that every device can have its own globally unique one.